So today we're going to do section 2.4, operations with functions. I think you will like this section. Much of this section operates just intuitively the way that you would expect it to work. So that's always helpful when things just work the way you expect them to work. So to start with, we're going to take a look at an example where I'm just showing you all the pieces. Could we get maybe Elizabeth or Kylie, one of you guys, if you could just turn that down? I think it's giving me a glare on the screen that's making it probably harder for you guys to see. Ooh, that's much better, I think, yes? Does that look better for y'all? No.
I think it's that one as well.
Think it's that one too? Then let's just turn those down a little bit too. I mean, I'll be writing in white, but still the screen itself with what's on there already is a little bit shadowed. Better? Wonderful. All right. Okay, so we have two functions given to us. F of x is x minus 3, g of x is x squared minus x. Those are just the examples we're working with. And the first example talks about what happens when we take f plus g of 3. So it works exactly like you would expect. What you do is you evaluate the function f at 3, and you evaluate the function g at 3, and then you add them. So my equation here for f of x, my equation here for g of x, will tell me what I'm doing. So f of x is x minus 3. So if I'm putting 3 in for x, it's 3 minus 3. G of x is x squared minus x. So I have 3 squared minus 3. And I realize I'm kind of overdoing the parentheses just a little bit for this one. We really don't need them here or here. But if it were a negative, we'd want to be really careful about that. So I'm just going to use them all the time so that we don't forget when the negatives come about. So we're going to do 3 minus 3. That's in the first set of parentheses, and that gives me 0. Over here I have 3 squared, which is 9, and then minus 3. And 9 minus 3 is 6. So this is 0 plus 6 for a grand total of 6. Works exactly like what we would expect. It says f of 3, I find f of 3. It says g of 3, I find g of 3. Addition happens between, so I add them. Does that make sense? Okay, so what I'm going to do is I'm going to do it just like that, and then I'm going to shrink them. And so that they're not changing my screen, they're not leaving my screen, but we've got them in a smaller space so I can do the next problem. All right, so on the next one, I've got the value 5. So I'm doing the same thing I was before, but I'm evaluating at the value 5. But this time, what do you think I'm going to do with my functions? Subtract them, I know. Yeah, that's exactly right. Exactly like what we'd expect, right? So we're going to find f of 5, and we're going to find g of 5, and we're going to subtract them. You don't really have to write this step out. I'm just reminding you that that's what we're doing. So if you don't write that, that's not a problem for me. But you do need to make sure you're putting them in the right locations, right? So in the first one, I'm putting the 5 in for x, so it's 5 minus 3. On the second one, I'm putting 5 in for the x, so it's 5 squared minus 5. So again, we'll work just like we did before. 5 minus 3 is 2. We do need to remember there's a subtraction sign that we're bringing down. And then I have 5 squared, which is 25 minus 5. And 25 minus 5 is 20. So I have 20 coming out of the second set of parentheses, but then I have 2 minus 20 instead of plus like I had last time. So I get negative 18.
Okay, I think you just said this. Where did the 3 come from?
Where did what 3 come from?
You said 5 minus 3.
The equation was up here. Let me highlight it in yellow.
Okay, gotcha.
Yeah, we're going back on all of these particular problems. We're going back to these equations. And those equations change, right? They're not changing on this example because I've set them up. But you'll have problem number 3, and they'll have one set of equations. You'll probably have number 5, and they'll have a different set. Yeah. Okay, any questions otherwise on that one? Okay, so again, let me shrink this and shift it up a little bit. Okay, and then our last one, on this slide anyway, has the dot between. That's telling us we need to multiply. So again, we're doing the same thing as before. We're evaluating. This time we're evaluating at the value negative 2, and then we're going to be multiplying. So this is going to be f of negative 2 times g of negative 2. And I'm going back up to the highlighted in yellow equations at the top. So this is negative 2 minus 3 times. And over here, I want to be a little bit careful, especially on this one. If you didn't use parentheses before, you really want them now. This is negative 2 squared, and it's minus a negative 2. So we have lots of negatives in this one. Lots of negatives. All right, so on the first one, negative 2 minus 3 is negative 5. Parentheses, not parentheses, doesn't really matter. On the next one, I have negative 2 squared, which is 4. And then I have minus a negative 2, which means what? I've got addition, right? So I've got negative 4. I'm sorry, I've got 4, and then I've got plus a 2. Okay, so I have negative 5 times, what's 4 plus 2? 6, and negative 5 times 6 would be negative 30. Okay, right, so everything's doing exactly what we would expect. So far, so good? Okay, we're going to continue with those same functions, but we're going to look at a few others. On D, we see division, right? All right, we did addition, subtraction, multiplication, division. Seems like the next one we should look at, so we are. And again, works the same way. It means I'm going to evaluate at the value negative 4, and I'm going to divide the results. So f of negative 4 divided by g of negative 4. So on the first one, I have negative 4 minus 3. That's evaluating at f of x. And then evaluating at g of x, so I have negative 4 squared minus negative 4. Again, lots of negatives. What do I get on the top? Negative 7. On the bottom, I have negative 4 squared, which is 16. And then I have, again, that minus a negative, so it's addition. So I have positive 4. What is 16 plus 4? 20. So I have negative 7 over 20. If it reduced, we would, but this one doesn't. Right? 7 and 20 don't have anything in common. Now, when we originally did those first 4 problems, they all had numbers that we plugged in for x, correct? Yeah. But they don't have to. They could say, like part E here says, f plus g of x. That's actually an easier problem. It just means I take the functions exactly like they are, namely f of x and g of x, and I add them. Well, f of x was x minus 3. G of x is x squared minus x, right? And we consolidate or combine like terms. Now, the parentheses don't end up being necessary here, but I did want you to see where they were coming from, so I wrote them. So what I really have, of course, is simply x minus 3 plus x squared minus x. And what combines? The x's. And in fact, they combine nicely to add together to be 0, right? So I'm left with, and you can either write negative 3 plus x squared or x squared minus 3 if you prefer. So I don't end up with a number at the end of this one because I didn't evaluate it at a number, right? It stayed x. So it makes sense that likely the answer will have an x in it as well. Okay, any questions on that one? Okay, so what's going to happen if I do subtraction? The same thing, right? I'm just going to subtract the two functions without plugging a number in. So I have f of x minus g of x. So that's x minus 3 minus x squared minus x. Subtraction, of course, is a little bit messier simply because I have to distribute the negative. So be careful when you're distributing here. So we're going to have the x minus 3, and then we're going to have minus x squared and plus x. Again, we look for anything that can combine. And what can combine here? The x's, but this time they don't cancel out, right? So if you want to write them in like the order that they go downhill, right, you're welcome to do the x squared first. It's negative x squared. I have 2 x's, and then I have a minus 3. If you just want to write them as they were from left to right, you could put that 2x at the beginning. That would kind of be a reasonable thing to do. Say I've got an x plus an x, there's 2x here, and I have minus 3 and minus x squared. The order is completely irrelevant. So this one did not collapse kind of as much as the last one did, but we're done. Any questions before I switch from slide? Okay. G has the multiplication and then H has the division, okay, again, with the arbitrary X in there. So we do them exactly the same way. This is saying I'm going to multiply. So I'm going to have f of x times g of x. F of x is x minus 3. G of x is x squared minus x. So what do we have to do on this one? FOIL, or distribute, right? We're going to multiply it all out. So if you want to do first, x times x squared is x cubed. The outer ones, x times negative x would be negative x squared. The inner, I have negative 3 times x squared, which is negative 3x squared. And my last terms is negative 3 times negative x, which would be a positive 3x. Okay, we've been multiplying things out now for over a month for sure. And then we're combining like terms. Which terms are alike? Yeah, the x squareds, they both happen to be in the middle as they're currently written. So I have x cubed all alone. What do I get when I combine my x squareds? Yep, negative 4x squared. And then I have the plus 3x. Sometimes when we combine there, or when we look at them, they don't combine. Like that's not something that happens. This one they did. Okay, is that one all right? Great. So let's shrink it again. So the last one I think that we have with these examples, that is this f of x and this g of x, is division. Again, nothing any different. It has this additional thing at the bottom that's talking about domain, so we need to do that before we finish this problem, sort of an extra step on the end. But I do have the function f of x on top of the function g of x. So f of x is x minus 3. And g of x is x squared minus x. Now, while it's true that I could factor the denominator, right? I can pull out an x and it leaves me with x minus 1. That doesn't actually simplify anything with the numerator, correct? Now, it's useful for the next step here in a minute, but it doesn't simplify anything any differently. So you can either leave it like this, or if you prefer to have it in factored form in the denominator, especially for our next step, you can write it like this. It doesn't make any difference. Both of them are equally right. The thing that happens with division, though, is that we end up with things in the denominator that often make the denominator equal to 0 in certain locations. So the reason they're asking on this one about domain is because of the division. There are values for x that are not allowed now because I've divided by that g of x. In particular, if you look at the factored form, either in our final answer on the far right or in the denominator part where I factored underneath, what values for x am I not allowed to use? 1 and 0. 3 is fine. It's okay to have a numerator equal to 0. So only the denominator we're caring about. So on the denominator, if you didn't see them right away, what we're doing is we're setting the denominator equal to 0, which sets each part of the denominator equal to 0. In particular, x is equal to 0, or x minus 1 is equal to 0, which gives me 1. So those are the two problems or two problem spots for my domain. So when I'm looking at finding my domain down here, I'll write it over here since I've run out of space kind of where it's located. I need to say that x cannot equal 0 and 1. That's the domain problems. So in other words, if I were given this and I did the division and then they were saying, okay, let's let x equal 5. You can do that. You can just put 5 into the final answer, either form of it. But if they said, let's let x equal to 1, you can say, no, I can't, right? Because it's not in the domain. 1 doesn't work. Okay, any questions? Okay, so that's the part of this that I think is very direct. If it says addition, we add. If it says subtraction, we subtract, and so on. It works exactly like you would expect. There is an additional operation we're going to look at, though, that's a little bit different. That operation is called composition. Composition looks like there's a little open circle between the f and the g. So it kind of looks like a multiplication symbol, but it's open instead of just being a dot. Okay? A lot of times people look at it and they say, well, look, it says fog. We'll see that. Okay, so this is the fog operation, if you want to call it that. I don't care. But anytime you see that open circle between them, it is not multiplication. It's just not. It would be a dot if it were multiplication. So what does it mean? Well, it means that we're taking a function and we're sort of embedding it inside of another one. So you see on the right-hand side, this second function, g of x, gets embedded inside of the function f of x. Okay, so it's called composition. It has this idea of putting it into something else. Now, the problems themselves aren't terribly difficult. You just have to keep all the pieces straight. So what I think makes it easiest is to rewrite it exactly like that every time. So over here, when I kept telling you, you don't have to write f of x times g of x. If you just want to move straight into it, that's fine. Over here, I think it's really helpful because I think that if you don't, you're probably going to get things backwards at some point, or you're going to try and multiply instead of actually compose or something like that. So every time I see this notation, fog, f composed g of x, whatever, I want to actually rewrite the second function inside of the first function, evaluated at whatever value it said. So this one was at the value 2. Okay, so over here, it said I'm going to take g of 2 and I'm going to put it inside of f of x. So that's the notation first. And then what we're going to do is we're going to work like order of operations from the inside out. Okay, order of operations always starts inside of the parentheses. So what's inside of the parentheses here is g of 2. And y'all know how to find g of 2. We did 4 of them at the beginning where we found f or g of functions, right? So of that specific value. So you know how to do that. You simply take the g of x function over here and you put 2 in it. So if you want to do that as a side step, you could. So if you want to write that over here, okay, let's just find g of 2, and I'm going to do that, and I've got the 2 plus 3, and you find, okay, cool, that's 1/5. You can do that if you want to do it as a side step. Okay, make sure it's still present on the paper because I need to see it, but you could do it as a side step. The other thing you could do is you could simply do it right here. Right? Sort of embedded inside of where it's located anyway. Either way, whether you do this part or whether you do it over here, what ends up happening is that your next step says f of 1/5. Right? Whether it's already inside or whether it's simplified somewhere else. F of 1/5 is what we have next. That's the second step. So now I take my f of x function. So that's the one up here. And I put 1/5 in for x. So I end up with the square root, right? Yes. Of 1/5, because that's where the x was. You don't have to have the parentheses, but that's what you're doing. You're replacing the x with the 1/5. Okay, so back to section P stuff, like chapter P stuff. We don't leave it like this. I mean, this is algebraically the right answer, but we're going to simplify it a little bit. Tori? Okay, we already did that. It was right here. Whoa. There's the 2. That was the 2 that went into the g of x function. So we replaced the x with 2. Now we take that and we simplify it, and it's simplified to 1/5. This notation does not say we evaluate f at 2. It says we evaluate f at whatever g of 2 is equal to. So I find g of 2 first, found out this case that it was 1/5, and then I evaluate the f at the 1/5 value. Okay, either in 2 steps or in 1. Either way, I do not get to leave this as the square root of 1/5, right? I need to simplify that radical. So this would be the square root of 1 over the square root of 5. Of course, the square root of 1 is 1. And then what do we do to rationalize that denominator? Yeah, we multiply the numerator and the denominator by that value. So this gives me square root of 5 on top. And what is the square root of 5 times the square root of 5? 5. So my final answer here looks like this. So I showed this one sort of in that embedded view. I'm going to do the next one where I just keep it completely separate so you can see kind of what that might look like if you were thinking about it from that perspective. But are we okay so far with problem? It's not 1, it's A. Whatever A is. Okay. So just like before, I need to shrink all this because it is really in my way now. Actually, I'm just going to shift it over. That will work. Okay. The next one actually has what looks quite similar, right? But the f and the g are switched, right? Okay, so this is actually telling us, and I'm going to actually write it underneath. Hang on. This is telling us that I take g and I put f of 2 inside of it. Okay, that's what the notation is. And believe it or not, it really does matter which one you do first. That's why you have to be careful that you're doing it in the proper order. This says that I'm supposed to do f of 2 first. So my first step, I'm going to find f of 2. It's the part that's inside. So f of 2 means I take my function square root of x and I put in 2 for it. So it's going to be square root of 2. So there's nothing to simplify or anything. It's just square root of 2. Step 2 says I take the outside function, the g, and I evaluate it now at the square root of 2. Okay? So the g of x function now has the square root of 2 in the location of the x. But that's this one. Is it 3 on bottom? Yeah. So it looks like that. Again, I'm not done yet, but does everybody see how I got to here at this point? Okay. Just like on the last one, I don't leave the square root in the denominator. I won't here as well. But I can't just multiply by square root of 2. I have addition in the denominator now. So how did we eliminate radicals when we had addition with radicals in the denominator? Remember? Yeah, do you remember what that's called, Noah, by any chance? Can anybody help him out? What was it? Not the reciprocal, you're getting close. Reciprocal means flipping things upside down. It's called the conjugate. So when you take the expression and just change the sign in between, it's the conjugate that you get. And the reason we do that is because it will perfectly eliminate that radical in the denominator, because the inside term, which will be 3 square root of 2, and the outside term, which is negative 3 square root of 2, add to 0. That's why we do it. Now on the top, I just have to distribute. Not that it's very exciting per se, but I do have the number 1 that I'm distributing. So I'm multiplying by 1. I do get square root of 2 plus 3. But in the denominator, I have to multiply the first terms together. So square root of 2 times square root of 2 is 2, right? Square root of 4, which is 2. And then at the end, I have the positive 3 times the negative 3, which gives me.
Sorry, what did it be? State, yeah, minus square root of 2 minus 3 because we're multiplying by square root of 2.
Oh, you mean on the top? Thank you. Yes, it would. That's better. Appreciate it. Yep, you're right. Square root of 2 minus 3 on top. Okay, so on the denominator now I have the 2, and then I have the 3 times the negative 3, which is negative 9. Okay? Again, the inner and the outer terms add to 0, which is the whole point, right? So those two, when I multiply them, give me the same value, opposite signs. So right here now I have square root of 2 minus 3. Thank you. And then 2 minus 9, which is negative 7. You can leave it just like that. There's nothing else that simplifies or cleans up because nothing has the same values like to factor out. Any questions on that? Okay, so that's with very specific numbers plugged in, right? So just like we did on the other ones, now we're going to look at what happens when we have just x in the problem instead of 2 or negative 3 or whatever the numbers are we've been plugging in. So they work the same way. I take f, because it's written first, and I put the g of x inside of it. Now, the difference with this one is that I don't have numbers specifically that are going to come out of this. I'm going to have some sort of a function, usually having x involved. So my g of x function is actually the same one I did before, 1 over x plus 3. So I'm going to take the location where I have this one, and I'm going to rewrite it as 1 over x plus 3. It's just a replacement step. G of x is 1 over x plus 3, so I write it where the g of x was. Now, just like with numbers, what this is telling me is to take the function f of x and to replace it with what's inside. It's just that what's inside is not a number now. So the function f of x is a square root function. And what I'm replacing x with is actually 1 over x plus 3. So this whole piece is in place of where the x was. Do you see the pieces being replaced? Wonderful. All right, so again, we're not loving leaving it like that. That's not a very pretty way to leave the problem. But we can leave it like that if we wish. There's a couple things we could do. The reason that we don't have to be quite so caring about the radical here is because that x value, depending on what it is, can actually give us something that is rational. So you can leave it like this. Right, if the x were like a 1. Yeah, if x were a 1 here, I'd get 4 on the bottom, right? And the square root of 4 would be 2. So because of that possibility, we don't have to worry about rationalizing. If you don't want to leave it that way, you could actually write it like this as another option. So it could be 1 over the square root of x plus 3. That's a perfectly legit way to leave it. Both of those are perfectly good options. Or you could multiply by square root of 3 over square root of 3. The square root of x plus 3 over the square root of x plus 3. And you could leave it like this. That's another option. All of these are places where you could stop. I myself is a fan of stopping sooner rather than later. So that's what you're going to see me do, like in my notes, on anything that's a test. I'm just going to expect you're going to stop there because you can. It's perfectly fine. There is an interesting thing that happens, though. Obviously, some values make this nice and it works out great, but there are some values that are simply not allowed, right? For example, x equals -4 is not okay here. Why? It can be a negative underneath the radical, right? So there are some values, much like when we did division earlier, that cause problems for this particular expression, right? I can't put just anything in. So it's either whether you're looking at it from here or from here. Those are your two places, or even from the last one is fine. There are values that I cannot let x equal. And in particular, what I need is my x values, not my x values, but my square root values to come out and to have only positives underneath the square root, right? And in fact, while zeros underneath the square root are usually okay, it's not okay here. Why is it not okay, for example, for x to equal -3? Because I have a denominator problem of 0. So I have two problems here. I have a radical problem and a denominator problem. Does everybody see that? Denominator can't be 0. The radical can't have negatives underneath it. So the reality is that what I really need is that x plus 3 to really be greater than 0. Not just greater than or equal to, like you could if it were just a radical, but also not equal to 0 because it's a denominator. This, you know how to solve. We've done this, right? We did this back in, I think it was 1.7. You subtract your 3 to the other side, and it tells you that x has to be greater than -3. And that, in fact, is your domain. X is greater than -3. Or if you wanted or were asked to write it in interval notation, that would be 3 to infinity. 3 to infinity. Right. I use the parentheses beside the -3 because it can't equal -3. Now, if in doing this you ended up with a radical and the radical were on top, then it could equal -3 and there wouldn't be a problem, right? It would be totally fine. Even if you've simplified it, so to speak, all the way to this very ending place, -3 still won't work because while it doesn't hurt for the numerator to equal 0, you would still, -3 would make the denominator equal to 0. So it still fails to be workable, right? Like I can't have it in any three of those different options. Okay, so we're going to do it in the other order now. We're going to take it and we're going to put the f inside of g. So I'm going to shift this over, and then we should be okay. So on the D, part D, we're going to take the g on the outside, and we're going to put f on the inside, because that's what it says to do. So inside here, f of x, well, f of x is square root of x. So I do a replacement, square root of x. And then I take my g of x function, that was the one that was over on the right-hand side, and where I have an x, I need to put a square root of x in, right? So I take this and I put it into this function right here. So I have 1 over the square root of x plus 3. again, there's really nothing wrong with leaving it like that, so I'm not going to mess with trying to play with it like I did in the last one just to show you options, because I don't need to. It's fine. However, I do have some domain issues. In fact, there's probably a couple of domain issues we need to be aware of. One issue, of course, is I can't have negatives underneath the square root, right? Okay, so that's fine. What's underneath the square root here is a little bit easier. It's just x. So I can actually have it equal to 0. That's okay. Because if I had 0 here, the square root of 0 is 0 plus 3. We're good to go, right? So one of the issues is I have a square root. The other issue is that I have the whole denominator. Is there any way that that denominator could equal 0? It can't. Why not? Right, so if I tried to set my denominator equal to 0, for example, this is where you were going with yours, and I moved my 3, what I would sort of have to eliminate is the possibility for a radical, a square root, to equal -3, and that doesn't happen, right? Again, I know some of you are thinking, wait a minute, what about that plus or minus thing? And you're right, but there is no plus or minus here, right? So if it's not there, it's just not there. There is no negative here. Now, if this question, I'm going to adjust it for just a second, not because it's my question, because I want you to think about what would happen if this here instead, I meant to do an eraser, were a negative. Could it work? Could I get a 0 in the denominator? Yeah, I could. And if that were the case, I would actually have to set this equation up over here, and I'd have to solve it and figure out what else x cannot equal. So I'd have square root of x minus 3. I would add my 3, and the x value would not be able to equal what? 9. So I'd have an additional value that I'd have to eliminate. Okay, so I would have an additional problem. Here I don't. So on this one, let's go back with what it was really supposed to be so that I don't have to adjust things that are wrong. For this one, the domain is simply that x is greater than or equal to 0. If it had been the other one, we would have had x is greater than or equal to 0, and we would have had x cannot equal 9, which you could write like that. If you were writing the interval notation for greater than or equal to 0, it's a bracket, 0 to infinity. If you were writing it for something like this, you'd have the bracket 0 to 9 with a parenthesis, and then 9 to infinity. Okay, so again, just use whatever the directions say. If they say interval notation, write it that way. Otherwise, you're welcome to leave it with just x is greater than or equals 0. Okay, so again, this was not my problem, but that's what it would look like if it were. Okay, we have one more thing to take a look at, and then we'll be finished for today. This was called composition of functions. We're taking two functions and we're sort of merging them together. We're taking one of them and we're plugging it into the other one, right? This is called decomposition. So it's taking something that's been mushed together and it's somehow separating it back out. Okay? So we need to separate out something that's already been combined. So they give us a function, f of x equals 3 square root of x, and then minus the 1. And they want us to find a g and an h that we can sort of separate them back out into. The interesting thing about this question is that there's often more than one right answer. There's plenty of wrong answers too, but there's often more than one right answer. So just because Tiffany gets a different answer than Kylie doesn't necessarily mean that either of them are wrong. So be really careful. Just because you're checking the back of the book and it doesn't match the back of the book doesn't necessarily mean you're wrong. You could be, but it doesn't necessarily mean. So I'm going to show you two different ways to do this problem so you can see what I'm referring to. Here's the thing you can't let. You can't let either of the two functions, in this case h or g, be x, because that doesn't break anything apart. All right? It doesn't do anything. It would mean that the other one was just simply the same f of x we started with. That doesn't break it apart. So what could you let it be? Well, notice that they're letting g be the inside function. So what here looks like it's sort of embedded inside of something else? The square root of x. It's a very natural choice. So one option is to let g of x be the square root of x. If we do that, then what I would need to embed it inside of is to simply replace the square root of x with x and put the other pieces around it. 3x minus 1. So if you were to imagine taking this and plugging it back in there, would you end up back with f of x? Yeah, you would. I think this is the most natural choice for this one, but it is not the only choice. There is another choice, one other, that would work here. Sometimes there's even more than two. The other thing you could do is you could let g of x equal 3 square root of x. If you did that, what would h of x be? X minus 1. And if you can imagine taking this and replacing it for x, do you get back to h? You do. So there are two valid decompositions for this particular equation that we are given. But again, what you can't do is this. So this is the no-go. If you write this down, write the big word no next to it and mark it out. I hate writing things on the screen and then trusting that you're going to mark them out. I'm going to mark it out on my screen. You mark it out on your paper if you choose to write this down. You cannot do this. You cannot say, well, let's just let g of x be equal to x, and then h of x is going to be 3 square root of x minus 1. One of the functions cannot be x and the other one be the thing we were looking for it to be. That's not okay. That didn't break anything down. So this is a big fat no. Don't do this. But the other two are perfectly fine. Any questions on those? All right, then we will end class for today. You have this homework 2.4 that will be due when you come to class on Tuesday.